All right, welcome back. Today is February the 9th, and I'm just going to take like 10 minutes to finish up NMR. I realized that in your NMR spectrum for the lab, there is a case for a double bond. We went over double bonds kind of briefly last time, so I want to take my time to like slow down. In my past experience, I teach double bonds for advanced organic chemistry. I never include that in this level. I think it should be enough for you guys to know the different splittings, the aromatics, peaks, the different functional groups. That's quite a lot, honestly. Double bonds, very rarely is taught in this level. But you were challenged with an unknown that has a double bond, and that threw me off. All right? So, to accommodate for that, I'm going to take my time to explain that. It's the reason why I don't like explaining it is because you spend more time explaining it, then later you just go, oh, that's a double bond. Oh, you see this multiply here and this over here, and then you say, okay, that's a double bond. But that's life. So and it's crazy because you have to explain it through a tree. There is, the NMR tree, and on your unknown, when you're solving an unknown, you don't have time to be doing a tree. All you want is to find out quickly what is the multiplicity, what is created this and that. Now, luckily, the unknown that you have has a simple double bond problem. All right, and I'm going to explain it here. So, let's take a look at this. So I'm going to copy this structure, and then I'm going to try to predict that proton NMR from my tree. All right? So I'm going to take this structure, put in here. I'm going to blow it up. And so basically, some of you, I taught this yesterday, but to the entire of you haven't. So the majority of you haven't seen this. So let's say I have this problem. And this is the simplest type of double bond problem that you will see. And this is exactly what you have in your unknown packet. So this is called a terminal double bond. Terminal double bond will have what is called geminal hydrogens, like twin hydrogens, because they're sharing the same carbon. So on a normal sp3 carbon, you say, okay, I have a signal here. This should be a singlet, all right? So, but that's not the case for the double bond. So when HA is by itself, and the same thing works for HB, when HA is by itself, it's singlet. But what happened? They're sharing the same carbon. A and B are sharing the same carbon. So B is going to say, okay, you know what, twin brother? We're going to take this shirt and duplicate this shirt so we can use it. Both can wear it. So they buy two shirts of the same kind, and now you have what will look like a doublet. So this signal will be a doublet. All right, this will be a doublet that will integrate for two hydrogens, because both of them will do the same thing to each other. Both of them will be a doublet, and so those two doublets will overlap to each other, and then it creates the same signal twice, but on the same signal. Kind of like the para hydrogens. A and B, A's are equivalent, so they have the same signal as a doublet. You mark that as A. The other one will be B. You mark that as two H's. All right, so that's a simple case. So now let's take a look at a little bit more elaborate case. All right, so if I'm going to predict, and this is all being recorded, if I'm going to predict the NMR shift for this, there you have it. You have a doublet at around, before 5 actually, around 4.8. And then this other singlet that you see here is the methyl group. So those two will be equivalent. You have a methyl group that integrates for 6. So you have 2 methyl groups there. So this is kind of like where you will see on your unknown. You'll have a terminal double bond. You will have a methyl group that is by itself, and then you have something connecting here to the other methyl, and then it branches out. All right. So that's what that goes. So now check this out. Let's take a different problem. Let's add one more hydrogen to that equation, or to that structure, I would say. I'm going to take this. I'm going to put it right here. And I'm going to process this, and I'm going to predict this. Predicting this is more elaborate, because now you will have 3 types of hydrogen. So in other words, the trick about double bonds is it kind of works like the W coupling in a way, but basically what you need to do is for each signal, do the n+1 rule to each neighbor. That's what you have to do. It's crazy. It's going to be extremely crazy. Check this out. So we're going to call this A, B, and C now. All right? So I'm going to start with the signal. Let's see. I wanted to do the same thing instead, but let me change this so I can. Let's call these A, B, and C. That's better for me, so I can see it better. All right, sorry about that. So I'm going to start with the signal for HA. The signal for HA by itself, it's a singlet. But then here comes C. Actually, let's not do HA yet. That's the most difficult one. I'm so sorry. Let's do HC. HC first. Yeah, that will work better. So I'm going to start with the signal for HC. It's the one below. That one, with respect to A, is going to have a broad, what is called J coupling. And so because it's trans, it is expected to be over 14, over 10, so around 14. Let's pretend it's 14. So HC with respect to HA will be split twice, and it'll have a J coupling that's approximately 14. All right. All right. So, all right. But then HC is also affected by HB. So what HB does is say, okay, you know what, twin brother, we are sharing this signal, so we're going to split it. I'm going to split you twice. Whatever you have, I'm going to duplicate because you're my twin brother. All right? And so now these J couplings are a little bit smaller. Let's say these are 7. And this J coupling will be about 7. And so, but the original J coupling is 14. And so now this signal for HC will be approximately something that looks like this, like a quartet, but it's not really a quartet. It's actually a doublet of doublets. And the difference, if you average from here to here, that J coupling will be equal to 14. Half of those two doublets, that's where you're going to measure that J coupling. So you know that this is screaming trans. This is a trans signal from the HC to the HA. All right? Now let's take a look at the HB signal, which is similar. the HB signal starts as a singlet, all right? But then HB is cis to HA. You see that? That relationship? Cis. They're on the same side. So because they're cis, they will have a much smaller J coupling. All right, so HB with respect to HA gets split as a cis. And now this J coupling is approximately, let's say, 7. And so it will be a much narrow double bond. It's going to form a narrower double bond. All right? But then HC say, bro, don't forget about me. I'm your twin brother. So we're going to split or duplicate. So it goes ahead and then duplicates. This will be HC. And now check out what's happening here. So this signal will be approximately, J will be equals to about 3.5. And this J coupling with about 3.5. And this is what you will have. Notice that this signal right here and this one will be in the vicinity or direction of this one right here, all three of them. So what you will expect is to have a little peak. You have a little peak, something that integrates for 3, and a little peak. This would be approximately what you will expect for this signal. Yeah. So this will be this actually, yeah, this will integrate. The integration for this will be integrate for 1 hydrogen, and the integration for this will integrate also for 1 hydrogen. And so this will be a cis. This will be your cis signal from HB to HA. All right, it gets even crazier here. Let's now do HA. HA start with a signal on its own without any neighbors. All right. Then for HC is going to have that long coupling on it. J is again equal to 14. Then HC will split HA in two times. It's going to duplicate it because it's 1 plus 1. It has one neighbor, so 1 plus 1 is 2. So it creates a doublet. And let me reduce this. And then HB comes into play and say, okay, you know, I'm also a twin brother. I'm going to split you in halves. And then here's where the mess starts. It's really messy. It's going to get really, really messy. And let's see if I can do this to scale. I'm going to try to do this to scale. All right. And again, this J coupling now is going to be around 7. And so this is the mess. Now, HA has 3 hydrogens here that are neighbors for D. Let's call this signal D. So D, hydrogens D, what are they going to do to each of those signals? It's going to split them into how many, you think? 4. Yes, 3 plus 1 will be 4. It's going to be messy. So you'll have 1, 2, 3, 4 signals here. 1, 2, 3, 4 signals here. And this is where you start like making a mess here. Let me make this a little bit smaller. So it's not going to be perfect for me, but Maybe I'll make this a little bit smaller. 1, 2, 3, and 4. 1, 2, 3, and 4. Holy macro. This thing's gonna be messy. Now you'll have this signal, this signal, this signal. Then you have 2 here. You have 1, 2, you have 2 here. You have 1, 2, you have 2 here. 1, 2, you have 1 there. All right, let's see what matches on the second and on the first floor, or the top floors. Second and third floor, I would say, because now we have the bottom here. So this signal is gonna look like, I'm gonna draw it here underneath so you can see it. This little signal will be one little peak. Then you have another little peak here. And then you have a third little peak right there. This is where it starts getting messy. Here you have 1, 2, 3 that are in the vicinity. So these signals will triple. 1, 2, 3. I'll put it like that. Then the next one will be a little peak, little dab. And then you have 1, 2, 3 again. You see that? This and that one on the top. They are kind of like on the same coordinates. That's going to be another peak, tall peak like that. Then you have another little dab, and then you have another 3 that are combining. And then you have that, it's going to be long, and then you have little. Here you expect to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 peaks will make this signal. All that to integrate for 1. All right, so that will all integrate to 1 hydrogen. And then finally, what happened here? Okay. And then finally, your 3 hydrogens on D will be a doublet because they have 1 neighbor on HA. So HD will be a doublet that will integrate for 3 hydrogens. You see that? All right, let's take a look at the actual NMR, or the predicted NMR. So if I do that and I go structure, protons, there you have it. There you have it. Check this out. Here's your doublet for D, around 1.72. And then remember that HC is the one on the top, right? If I hover over it, so let me do this. Let me hover over it with my mouse. So if I go here, it tells me which one is down there. You see it in green? Let's blow that up. Let's blow that up. There you have your 13 peaks. Not quite as nice. I didn't draw it quite as nice, but they are 13 peaks, and I can assign that. Check that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 peaks. This looks nicer here. Of course, computerized. Mine is shaggy. But here you have your other 2 signals. This one right here, the one on the left, you see is narrower. That is your cis. That is your HB. The one on the right side, the 2 peaks on the right side, that will be your HA, right? The one that is trans to HC is wider. This J coupling is wider than this J coupling. And both of them are doublets that integrate for 1 hydrogen. So what I'm saying here is, let me lower this. Look at how it turns green underneath. If I hover over here, this one is my trans. See, that is the one on the right side, and green. If I hover over the one on the left side, It goes to the left side. That is HB, the one that produces a J coupling of around 7, half of the trans. All right. So this is how you would do double bonds. And this is what I'm saying. Like on your unknown, all you care about is, oh, I have a multiplet. And that accounts for 1 hydrogen. So I'm dealing with double bonds. And they are between 5.5 to 6.5. Your unknown was harder because that double bond, when it's single, actually shows around 4.5. It's kind of hard to predict. But remember the other predictor? That kind of predicted it too. This one. That was going to be actually before 5.5, which is what we have on the table for NMR. So here's your doublet, and they all, it will be for these 2 signals here. All right. Let me stop here. And so, yeah. Any questions about this? Understood? Good. All right. So now if you have check this out. If you have a methyl group here, for example, then instead of being this signal being a quartet, now it's going to be a triplet. So you have to triple up the last portion, like this one right here. You have to triple up here instead of quadrupling up. You see what I'm saying? And so you will get less peaks. So you still have to count the ones that match from the top, and that way you can figure out how many peaks you will actually have. All right. So, but you don't have to worry about that here in this class because I'm not gonna test you on that. If you were on my advanced OCHEM class, then I will. But I feel that you know enough for your OCHEM 1 and 2. So, all right. So I'm going to stop here. And I'm going to start mass spec. All right. So what I'm going to do today is I want to talk about the major type of fractions. And then on Thursday, we'll practice one of the practice homeworks. I will teach you some more mass spec in the lab this week. So you won't be too lost, I think, hopefully. All right. Why do I need to do this? Because it's important for me to at least point out what are the most important fractions, how they're happening, that kind of thing. Then at 10:15, I'm going to stop to give you the quiz so that you'll have 20 minutes to do your quiz. That good? If you need a little extra 5 minutes, you can stay a little longer. And then transition into the lab, you'll have total 25 minutes. Okay? But please, someone, don't be shy. Say, Dr. Oden, it's 10:15. All right? So I'll know, okay, that's my cue. Then I'll stop what I'm doing. And then we transition into that. All right, mass spec. We're going to go back to the beginning of chapter 13. And I'm just going to give you a brief overview. I'm not going to be writing too much because I'm writing it for you. We're not going to reinvent the wheel. But basically, imagine mass spec and compare it to when you were playing pool. All right, so you're playing pool. You're going, oh, this is a good, so you're playing pool, and you're going to hit the white ball, right? And that's going to strike the colorful balls. So your white ball represents the electron beam on the mass spec. So you have an electronic beam which is caused by a lamp. So it could be like a lamp of sodium or something that is throwing electrons. And that collision is going to be a random collision. That's why you have several different kinds of fragments. All right? So, so if I want to represent the collision here, here's my electronic cloud. This is my molecule. My molecule is neutral. mass spec only identifies ions, and they need to be plus charge or minus charge. You can also do minus charge, especially when you deal with carboxylic acid. You have to switch the mass spec mode to negative. It's something that I had to learn when I was doing research. But most of the time, you keep it positive. Okay. If you're dealing with anything that other than carboxylic acids, it'll do well in the plus. One thing about mass spec. So when you're doing mass spec, you have to basically keep an account of everything mathematically. Basically, that's what it is. All right, so I'm going to knock one electron out from this molecule. The most easier electrons to knock out are your non-bonding ones. So that's the first thing that's going to be knocked out. They are like standing there outside, they're not making any bonds. They're the easiest one to knock out. So if these are non-bonding electrons, this electron beam is going to go ping, take one of them out. And that electron gets ejected, and then you get a plus. You get a plus ion. All right? If you just knock out one electron from your molecule, that is considered the molecular ion. And it's designed as M+. All right? Some mass spec, this is the thing I was going to say. I was trying to just my memory. Some mass specs will give you results as M+1. Sometimes when you use sodium lamps, you have to add +23 because the sodium plus will attach to your molecule. So all those little things you have to learn, but most of that you learn from research and experience. So we're just going to give you the basics here of how the mass spec works. When you have a plus and minus, a plus and radical, this is it's called a radical cation or a cation radical, depending on how you want to read it. And they're short-lived, unstable, and the fragments usually result from these collisions. All right, so you have the non-bondings. Then the next type of electrons that you can knock out are the pi bonding electrons, because those goes next on the energy ranking. So you have non-bonding on the top, pi second, and lastly you have the sigma bond electrons. So for the pi electrons, you can also eject an electron like that by kicking it out. This is exactly, and let's call this direct hit. How about that? So we're going to do a direct hit on one of those electrons. All right? I like to call it like that, direct hit. There might be a different terminology, but that's good enough for me. All right? So I don't think I should go through this, so let me skip that. Basically, let me go through it. 10 cents application of the mass spec. You inject your sample. It goes into an electron beam chamber. That's where the collisions start. Then you have a slit here where only those molecules that have been hit will go through. And then at this point here, you have fragments, you have molecular ions. So they are all those ions are moving around here. And this curvature here with the magnet help them to separate those fragments into the final detector. So the detector is going to catch them here, but they're separated now by the molecular weight. So the lighter ions will be showing up, actually they're going to be showing up early in the mass spec, and the heavier ones towards the end of the mass spec. And that's why you read the lighter ions from left to right in the mass spec. All right? And so, let's see. Yeah, so that's good enough for theory for this. All right, let's move on. And my emails, my videos have a little more extra. All right. So very important fragments that you will need to recognize. The easiest one to recognize is the N plus ion. That's your molecular ion. If I ask you to pick 3 or 4 fragment ions from a molecule, don't forget to include the N plus ion, because that gives you points right away. All right. The second most important then is the base ion. This is the peak with the greatest abundance, and it's always the tallest peak. That's how you recognize the base ion. All right. Now this for the lab, because I am asking this question on the quiz. So remember that. Another little punt there for you guys. The base ion is usually the most stable ion form. So how do I know which one is the base ion? So what I have observed with experience is we're going to learn that. Look for the different fragmentations that give you the most possibilities to make that fragment happen. So say, for example, you have, let's see, I had that molecule here. Great, I have it here, yes. Hold on a second, let me show you something that I was working this morning on your pre-lab. Check this out. I'm going to help you out for your pre-lab too. So if you want to, you can take notes. Check this out. Why do I know how to predict the base ion? So there was a question on let me see, what's the question for that? Give me a sec, because I want to help you out with this. It says, in the mass spectrum, the following compounds, which is the tallest peak at mass charge ratio of 57 or the peak at mass charge ratio of 71? All right. So the question is, which of these? So if I have a mass charge ratio of 57, which one will give the mass charge ratio of 57, and which will give the mass to charge ratio of 71, based on A, 3-methylpentane, or 2-methylpentane. So I'm going to explain this so that when you get to the lab, you're not too lost. All right, so let's draw this molecule. Pentane, 1, 2, 3, 4, 5. 3-methyl, right there. 2-methylpentane, pentane, 1, 2, 3, 4, 5. And there will be 2-methylpentane here. So this is how you can predict the base ion, based on probabilities. If you have a bond that can be broken, and it gives you in two different positions, or if you can break 2 bonds, that will give you the same fragment, you're increasing your odds by 2. All right, your chances have been doubled. What I mean by that is, if you were to break, say for example, I had the sigma electrons here. If I hit this guy right there, and so what is the mass of 3-methylpentane? Let's see this. So this will be C 1, 2, 3, 4, 5, 6, C6, H14. The mass for that will be what? 6 times 12. 6 times 12 is 72 plus 14. That's 86. So if I lose an ethyl group, how much am I losing? So 86 minus 29. Yeah. So an ethyl an ethyl group will be a CH3 with a CH2 group here. Whether it's plus or the radical, doesn't matter. You have C2, that's 24. 24 plus 5, that's 29. So I'm losing a fragment of 29. So I got 86 minus 29. This is equal to 57. Check this out. You can do that breakage here or here. Bling! See that? And you increase your chances by 2. Therefore, 3-methylpentane will most likely have a base ion equals to 57. How cool is that? Now let's check out 2-methylpentane. According to the probabilities, I see 2 methyls. If I get rid of one or the other one, doesn't matter. But I'm increasing my chances by 2. That is going to be my base ion. No other fragment will produce the same fragment ion unless I get rid of those 2 methyl groups. Hello. And so the possibilities here are the same. Here you will also have, again, you will have a mass of C6H14, which is equal to 86. Now, if you get rid of this this electron, or this one, you will increase the probabilities by twice, by 2. All right? So how much is 86 minus a methyl group? How much is a methyl group? 15. CH3, whether it's radical or CH3 plus, that's equal to 15. So minus 15, there you have it, 71. So the base ion for 2-methylpentane, based on probabilities and statistics, it will be equal to 71. Make sense? That will be your tallest peak on the list. Yes, sir?
Could you also talk about carbocation stability?
Yeah, carbocation stability. Very good. So notice that in this case, any fragment that you make here from these 2 molecules will be secondary carbocations. All right. So if you let's say you do this one right here. Let's do this one because it's easier to me. So I'm gonna have 1, 2, 3, 4, 5. I'm making a plus right here. This is a secondary carbocation. That would be better than, for example, this one. This one would be a primary carbocation. All right. This one right here, when I lose this ethyl group, I'm gonna have a plus right there. You see that? And this is a secondary carbocation versus this one. Well, this will be a radical. But let's say if I kick this one out instead. So when you're doing the direct hit, what I call you have 2 options on a bond. You can hit the electron on the right or the electron on the left. Here I'm kicking the electron on the first. I'm going to kick the electron on the left, and I'm going to produce a radical here on the ethyl group and a plus on the secondary carbon on the butane fragment here. Now this is a butyl fragment, which will be so it will have a mass of 57. All right, this will have a mass to charge ratio of 57. All right. If I do a direct hit here in blue to that one, then I inverse the roles. Then I will make a radical here and a plus ethyl carbocation. And this one will be unseen, and this one will be seen in the mass spec. So you will have both. You will have both. And on the other hand, this one will be seen, and this radical will be unseen. or undetected in the mass spec. Any questions up to this point? I forgot to take the picture. Oh, lucky you. I want to take the picture before I proceed here with a panoramic picture. All right, please look at the camera if you don't mind. It's going. I'm taking the panoramic. There's my man, Jeff. All right, thank you. Is Ashland here? Yes, she's here. All right. Oh, that's okay. Hey, it happens. Hey, you're welcome here at any time. That door is open. I'm just worried. You know what maybe I shouldn't say this on recording, but let me record this. Let me stay. So what time is it? Oh, we got a few more minutes. So let me continue here. So this slide just tells you why is mass spec useful for. We also have high resolution mass spec, where, for example, the usual mass spec that we have gives us these numbers, and you cannot tell which one is which. But with high resolution mass spec, then you get more decimals, and that gives you the exact molecular weight of the compounds. All right. So there are isotopes you have to consider. So the chlorine atom gives you two isotopes. One that is 35, has a mass of 35, chlorine 35, and the other one that has a mass of chlorine 37. All right, so you're going to differentiate them because the mass ion will be the 35 one, and then next to it there will be a little stump that is 1/3 short, like 2/3 shorter than the mass, than the N plus, and so that's your isotope of chlorine, which is N plus 1. N plus 2. I'm sorry. So you have the N plus and the N plus 2 in a 3-to-1 ratio. And then for bromine, you have two isotopes. You have the one on 79 and the one on 81, and then the ratio is 1-to-1. All right, roughly about the same height. We're going to go through examples, so I'm not going to go through this right now. Actually, this example is kind of cool. I started off giving you the molecular formula, and then you go from there. You figure out that you have a DU of 4, that kind of thing. Kind of similar to proton, but let me speed up a little bit because I want to do problems. Yes, so this is the thing. This one, the moment that you have a molecular formula of bromine, you can then predict that you're going to have your 1-to-1 ratio of N plus. Notice that your N plus ion is actually your base ion 2 here, because it's the tallest peaks. So this is both N plus 2, and base ion. So your N plus happens to be your N plus and your base ion. All right. Notice that the N plus is just a little bit, just a bit higher than the N plus 2 in bromine. And don't worry, we're going to practice how to calculate these fragments today in lab and in class. Actually, nitrogens, one atom of nitrogen will give you an odd number. Whenever you see an odd number present, you are dealing with a nitrogen. That's a really good cue to figure out when you're doing unknowns. And I think I'm getting close to my stopping time here. So there's 3 common possibilities. You have the non-bonding collisions with the electron beam. Then you have the pi collisions and the sigma collisions. Let me explain you this one. This one is hard to understand. I'm going to take 1 minute to do this. This is big. So most of the time, your alkanes are represented with a bracket, and your cation radical, plus and the radical here. And so when I was a student, I asked my professor if he could explain me this, and like, he said, like, just learn it like this, memorize it like this. I was like, that's not enough for me. So I realized that this is what happens. So let's say you have propane here, and you're gonna knock one sigma electron. So I'm gonna choose the one outside, the one with the hydrogen, because they're surrounding the carbons. It's harder to, but it's not impossible. You could hit this sigma bond and get rid of one electron. But I'm just gonna get rid of this electron. So I'm gonna get rid of that electron that is right here. Bling! And I'm gonna form a plus radical, my cation radical structure. And because this is plus and the radical is mostly negative, right? They're gonna travel together. But unbonded, they're gonna be traveling together. And that's why the mass spec detects it like that. All right? And I think that I'm satisfied with that discovery. And so that's how I teach it. All right, so we're going to take the quiz now. I'm going to stop the recording. When we come back on Thursday, we will do the 4 different kinds of fragments: the loss of water, the alpha cleavage, the direct hit on an alkane, and also the McLafferty. And then we'll do a packet, and then we're wrapped up mass spec. Okay. All right. So let me close this. Please get ready for the quiz. It's super duper doable. Oh yeah, pull out your NMR chart, your infrared chart, if you have the one from the notes, okay? And if you don't have the infrared chart, you can still figure it out without it. Honestly. All right. So I'm gonna do this. I think I'm gonna keep one because I think I have extras. But please pass this along as fast as you can. Pass this to the right. And any excess given to me, I'm going to use this, pass that around, and I'm gonna start here. Pass this around, and give me the extra. Thank you. One extra. Oh yeah, that's fine. I don't think you guys say cheap, honestly. So it's an unknown. Give me any excess paper. But you have it. No, you see what's going on to the left. So how do you do it? Anybody need to know? You didn't get one, you are accepted. All right. Yeah, you still want it. Do it open book. Doesn't matter to me.